Now, one of the things that is so important to remember about volumes of revolution is that we were really just finding the volume of a cylinder, pi r squared h, where the height was dx, and then we were integrating that. And why that's so important is because it allows us to do other shapes as well. So we're going to find the area in the first quadrant, bounded above by the function 1 minus x squared and below by the x-axis on the interval from 0 to 1. It's the base of a solid with cross-sections perpendicular to the x-axis. So you can see a kind of a three-dimensional look at this. Of course, 1 minus x squared just looks like this, and we're talking about this area being used. And as I said, you can kind of see a three-dimensional shape. Well, the little squares here, of course, near 1, they're very small. You know, we got base times height. Remember, in a square, the base and height are the same. And of course, as we get closer and closer to 0, the squares will get larger and larger because the base will be bigger. Now, how I always think about this is I start by just thinking about the face, okay? Just the face of the, like this, and I say, okay, it's a square. The area of a square is the base squared. Base times height, but the height is the same. So if I then add a third dimension to this, which you can see kind of sketched in, that there are all these little, prisms, square prisms. Well, the volume now of that square prism is the base squared multiplied by the, thickness. But for us, that's dx. Well, then the question is, well, how do you get the base? Well, the base is dependent on the function. Here, the base is very small, where back here, the base will be very large. So we do a little substitution, and we say, well, the base is set by the function. So here we are. The base is, or the volume is area of the square multiplied by thickness. And similar to what we did with the revolution, now we integrate this. So we're going to integrate 1 minus x squared dx. Our bounds are 0 and 1. And we don't need a pi or anything on this because, of course, this isn't a circle. It hasn't been revolved. The area of those circles, when we did revolution, was pi r squared. But this is a square. So there's obviously no pi necessary in this. Okay? If you needed to do this by hand, of course, I would recommend actually rewriting it as 1 minus x squared and 1 minus x squared, and actually multiplying it out and then integrating it. Otherwise, you could use fn int. For the interest of time, I'm going to stop there and rely on the fact that you could, in fact, do that. Now, in this example, an area is bounded above by the function square root of x, below by the x-axis from 0 to 3, and we have semicircle cross-sections perpendicular to the x-axis. So again, remembering what the square root function looks like, that from 0 to 3, you can see, I think, a nice three-dimensional representation of what those semicircle cross-sections would look like that are being built off of that base. Okay, so these are a little different, as I said, than revolution in that we're making our shape the base of a solid. So again, I always I draw the shape of what the face would look like. It's a semicircle. And then I think, okay, the area of a semicircle is 1/2 pi r squared times, I'm sorry, it's just 1/2 pi r squared. So this is three-dimensional though. Okay, so now we say, well, the volume then is the area of the base multiplied by the thickness, which is just dx. And where this one gets a little bit tricky is I want you to think about, it made sense, I think, in the previous one that the function set the base. Well, I mean, the function is, that blue line. The square root of x sets that base still, but that is not representative of the radius This represents the diameter. So to get the radius, we need to divide it by 2. So this equation becomes 1/2 pi multiplied by the square root of x over 2 squared dx. So we integrate. Of course, this one will be from 0 to 3. I would put the 1/2 pi out front. They're constant multipliers. And then I would just have the square root of x over 2 squared dx. Now, one of the most common mistakes in this when people look at this is they say, you know what, I don't understand why I had to divide by 2 twice, and maybe I shouldn't have. You're absolutely right dividing by 2 twice in this problem. Let's just remind ourselves what each one means. The 1/2 pi out front, this 1/2 comes from the fact that it's just a semicircle. Okay, we're not finding the area of the whole circle, we're finding the area of only half of a circle. The dividing by 2 inside here comes from the fact that the function does not represent the radius, it represents the diameter. So we had to divide by 2 again. Now again, if you had to do this by hand, you certainly could, write square root of x squared is x, 2 squared is 4. Then you could even bring the 4 out and have 1/8 pi out front and just have an x dx inside like that, and then finish that off. And again, I'm going to rely on the fact that you could do that integral.